For this lab, a soccer ball will be dropped from rest, rebound from the collision with the ground, and then come to rest once again at the pinnacle of the rebound height. Using tracker software, we will analyze this motion and compare it to a computational model that recreates this motion. The objectives of this lab will include recreating the motion of the ball using Newton's second law of motion for the falling and rebounding of the ball, monitoring the changes in energies of the ball using the energy principle to see if it is satisfied, finding the internal energy of the ball due to the collision, and then finally deciding how elastic the collision was that occurs between the ball and the ground. Here we can see the ball falling from rest and then rebounding to a height less than the original. The motion of the ball in the y direction over time in this plot shows the same results in a more detailed fashion. Since the ball does not bounce back to its original height, we know that the collision was inelastic, but we will continue to find how close to elastic the collision was. So before creating the motion of the ball using VPython, we must include the mass, initial position, and initial velocity of the ball before the ball is dropped. In order to make the ball bounce, we will need to implement two loops that create the motion. First, one for the falling of the ball, and second to show the rebound. Here you see the initial velocity is 0 since it starts at rest. After the falling loop, we must reset the initial velocity of the ball once the ball rebounds, so this second initialization is needed. Using the tracker data, we can find that the initial upward velocity of the ball after hitting the ground was 4.4 meters per second. For both loops, however, after the initial velocities are set, Newton's second law can be used to track the motion of the ball using the net force of the ball equaling the only force, weight, acting on the ball over the falling and rebounding segments of its path. So for both loops, we implement Newton's second law as seen here. After all of the code is set up, we can see that our computational model, in red, predicts fairly well the motion of the ball as observed in tracker, in blue. The motion in the y direction over time is seen here in this graph. The ball doesn't perfectly track the motion of the tracker results, but this could be due to the blurriness of the tracker video and the misplacement of the center of mass of the ball. However, it is definitely modeled fairly well based on Newton's second law, and in this time period, air resistance was negligible and the terminal velocity was not reached. For the second objective of this lab, we were observing the energy principle over the course of the ball's path. In this case, the ball and the earth will be considered as part of the system and no external forces will be acting on the ball and the earth. Therefore, the change in the total energy of the system will be 0. The components that make up the total change in energy are the change in kinetic and gravitational potential energies. The initial kinetic energy of the ball is 0, since it is at rest, and the change in potential gravitational energy will be calculated as seen. So initially, we calculate the gravitational potential energies in VPython for the ball at rest. Then, for the loop where the ball is dropping, the final kinetic and gravitational potential energies are calculated after the model moves during the time step. The initial energies are subtracted from the finals, and the total energy change is found for each time step. We are expecting the change to be equal to 0 to satisfy the energy principle. For the second loop, which recreates the rebound, the energies are found using the same formulas as before. Once again, they are used in VPython as seen here to calculate the energies. When the energies are graphed based on time, we see that the change in kinetic and gravitational potential energies increase in magnitude before the impact and then decrease in magnitude after the ball rebounds. This is what we would expect since the velocity of the ball increases when falling and then decreases when rising back above the ground, since its change in momentum is always in the negative y-hat direction. Based on this graph, we see that the energy principle seems to be satisfied since the change in total energy of the system remains at 0. In finding the internal energy and elasticity of the bounce, we must analyze the ball's kinetic and potential energy right before and after the collision occurs. Based on the model created, the kinetic energy of the ball at the time step right before contact, the kinetic energy was slightly larger than the kinetic energy after the bounce. The change in kinetic energies and the gravitational potential energy changed by small amounts and in opposite directions. Based on the energy principle, the change in the total energy before and right after the collision should be equal to 0. However, we see that this is not perfectly satisfied. Therefore, there must be an internal energy gain of the system. Even though it is small, there is an internal energy increase in this scenario. Finally, the last objective of this lab was to see how elastic the collision was of the ball hitting the ground. In any scenario, an elastic collision results in no change in kinetic energy. However, as we calculated, the change in kinetic energy for the collision was not equal to 0, and there was a loss in kinetic energy. Therefore, the collision was inelastic, but it was not maximally inelastic since the ball did not merge with the ground. What does it mean? Since there was a change in the internal energy of the system of the ball and the earth, where did it come from? As you can see, when the ball collides with the ground, the ball deforms quite a bit, and therefore energy inside of the ball slightly increases. Also, there could have been a small increase in the thermal energy of the ground and the ball. What if the ball had an elastic collision with the ground? What would the motion of the ball rebounding off the ground look like? If the ball were to have an elastic collision with the ground, the change in kinetic energy of the ball would have been 0, and the ball would would then have the same speed traveling upwards as it would downwards at any given y position. If we replace the initial velocity of the ball moving upwards as the magnitude of the ball just prior to the impact in the opposite direction, then the ball would move as seen here. Also, we can see that the change in the kinetic energy of the ball would be 0, since the initial kinetic energy would be equal in magnitude to the final kinetic energy of the collision. In conclusion, Newton's second law could be implemented in 2 loops to recreate the motion of the ball. There were slight differences which come from the misplacement of the center of mass of the ball, or error in the calibration stick's accuracy. Also, the energy principle is seen to be satisfied when the internal energy of the system is considered. This internal energy shows up mainly due to the deformation of the ball and then slightly to a very small increase in thermal energy of the system. And finally, we found that the ball's collision with the ground was inelastic, since the change in kinetic energy before and after the collision was not equal to 0. Thank you for watching.